All right, let's talk about something that sounds a little crazy, a paradox that connects your breakfast to actual geology. It's called the limestone paradox, and it's all about how the very same mineral from the very same rock can have completely opposite effects on two different kinds of chickens. Yeah, you heard that right. What builds one up can actually weaken the other. So let's dive in and figure out why.
At the heart of all this are two things that are absolutely critical. Strong bones for the chicken itself and strong shells for the eggs it lays. And guess what? Both of them depend almost entirely on one single mineral, calcium. But here's the trick. Getting that calcium from the feed into their bodies in the right way, well, that's one of the biggest challenges in all of poultry science.
So that really brings us to the big question, doesn't it? That omelet you had for breakfast, or maybe that roast chicken for dinner. The quality of both of those can be traced all the way back to, of all things, the type of crushed rock in the chicken's feed. How is that even possible? Well, it all boils down to a really fundamental problem in chicken nutrition. And that problem, it's the fact that, not all chickens are the same. Not by a long shot. We raise them for two very, very different reasons, and that creates two completely different biological needs.
So on one hand, you've got your broiler chicken, the one bred for meat. Its entire job is to grow incredibly fast. That means it needs a constant supply of calcium just to build a skeleton strong enough to hold up all that weight. Then, on the other hand, you have the laying hen. Her skeleton's already built, but every single day she has to pull a massive amount of calcium out of her system to create a hard, protective eggshell. So two different jobs for the exact same mineral. The question is, can the same solution possibly work for both?
Let's put on our detective hats for a minute and look at our first case, the growing broiler chicken. For a long time, the thinking was that a slower, more sustained release of calcium had to be better, and that means using bigger, coarser chunks of limestone in the feed.
And that leads us to our first big hypothesis. The theory went something like this. Coarser limestone would be easier to digest and would help these broilers build stronger bones, especially if their diet wasn't perfectly balanced to begin with. So naturally, researchers decided to put that idea to the test.
Okay, so here's how they set it up. They took more than 1,000 broiler chicks, and after about 2 weeks, they split them up into different groups. Each group got its own special diet. Now, they were really only changing two key things. First, the size of the limestone particles. Was it a fine powder or more of a coarse grit? And second, the ratio of calcium to phosphorus, the CAP-P ratio. That ratio is a super critical recipe for bone health, and getting it right is everything.
So here's the main difference you need to get. Fine limestone is like a quick hit of calcium. It dissolves super fast in the gut. Coarse limestone, on the other hand, is kind of like a time-release capsule. It hangs out in the gizzard for longer, dissolving slowly and providing a steadier supply. The theory was that this slow-release version had to be better for building strong bones. Makes sense, right?
So, the million-dollar question, was the theory right? Did those bigger particles actually lead to bigger, stronger bones in these fast-growing chickens? Well, the results were definitely not what anybody was expecting.
Yeah, the hypothesis was just completely wrong. Busted. It turns out the size of the limestone particles made almost no difference to bone strength. And get this, at high calcium levels, the coarse limestone was actually less digestible than the fine stuff. The one thing that truly mattered, the variable that made all the difference, was the balance, that ratio of calcium to phosphorus.
And this chart just shows it perfectly. We're looking at the strength of their main leg bone, the tibia, measured in newtons. Now just look across any row, from left to right. See? Fine limestone versus coarse limestone, the numbers are pretty much the same. But now look down the columns. When you change that K/P ratio from a low 0.50 up to the optimal 1.00, wow. The bone strength just jumps from around 140 newtons all the way up to 216. That is a massive difference. So for broilers, the takeaway is crystal clear. It's not about the size of the rock, it's about the recipe. The magic number is a calcium to phosphorus ratio somewhere between 1.00 and 1.25. That is the sweet spot. That's what gives you the best bone strength and growth. But what about our other chicken? Okay, let's switch gears and open up our second case file, the laying hen. For her, this is a whole different ballgame. She's not trying to build a new skeleton, she's desperately trying to hold on to the one she's got. So, could that coarse, slow-release limestone be the hero of her story?
To really get this, you've got to think of a hen's bones like a bank account. She can make deposits, that's bone formation. But every single night, when her body is forming an eggshell, she has to make a huge withdrawal. That's bone resorption.
For the longest time, the big question was whether a hen could ever really get ahead. Could she make more deposits than withdrawals once she started laying? Or was she just fighting a losing battle, doomed to a slow decline in bone strength? This is exactly what the second study looked into, focusing on calcium intake and how soluble the limestone was, which, remember, is tied directly to its particle size.
And the results here were just striking. This chart shows us the bone strength of hens near the end of their laying cycle. Okay, so the hens on a lower calcium diet with that fast-release, highly soluble limestone, their bones could handle about 10.7 kilograms of force. But look at the hens who got more calcium from a slow-release, less soluble source. Their bones were almost 10% stronger, breaking at 11.8 kilograms. That's a big deal.
So, for the laying hen, the verdict was the complete and total opposite of the broiler. The slow-release pill was exactly what she needed, giving her that steady overnight supply of calcium from larger, less soluble particles was absolutely critical. It meant she could build that eggshell using the calcium in her gut instead of having to raid her own bone bank every night.
So we have these two findings that seem to totally contradict each other. Let's put the pieces together and solve this puzzle once and for all.
And here it is, the limestone paradox solved. For the broiler chicken, growing at lightning speed, it's all about the chemical balance. That C/P ratio is king. The physical shape of the limestone is just a minor detail. But for the laying hen, who faces a calcium crisis every single day, the physical form is everything. That slow-release source is what gets her through the night without depleting her own skeleton.
And look, this isn't just some interesting science fact. Getting this right matters in the real world. It means stronger, healthier birds, a huge win for animal welfare. It means better quality eggs with shells that don't crack as easily, which means less food waste. And it means we're using our resources more efficiently, which can save money and is better for the environment.
What I find just amazing is this conclusion from the hen study. It proved that, contrary to what a lot of people used to think, hens can actually increase their bone mass well after they start laying eggs, all the way up to 50 weeks old. They aren't just managing a decline. They can actively build up their reserves, but only if they get the right amount of calcium in the right form.
It's just such a powerful reminder that in biology, the tiniest little details can have these huge, profound effects. The difference between limestone dust and limestone grit can completely change the life and productivity of an animal. It really makes you stop and wonder, doesn't it? What other simple, elegant solutions are just hiding out there in plain sight, waiting for us to look a little closer?